In this video, we will cover the first few reactions of aldehydes and ketones, including acetal formation, imine formation, also related as the Wolff-Kishner reduction. We will be talking about enamine formation, as well as the hydrolysis of acetals, imines, and enamines. With acetal formation, we will be looking at aldehydes and ketones reacting with oxygen-containing molecules. So the oxygens will be acting as the nucleophiles and attacking the carbonyl carbon. So for example, we would take an aldehyde or ketone, and I'll go ahead and use a cyclic ketone as our example, and we will be reacting it with an alcohol or water. We're going to be focusing on using weak nucleophiles. So I will use methanol as our example. This mechanism will run under acidic conditions, so we will have a little bit of acid involved. And ultimately, we will form a product that looks like this. So this is an acetal. And an acetal is when you have an OH or an OR group, and you have two of them attached to the exact same carbon. So this is our definition of an acetal functional group. Now we will also form water as a product. Now when the nucleophile is water, the product actually has a slightly different name than an acetal. It's actually called a hydrate. Now the mechanism for acetal or hydrate formation will be exactly the same. On the next slide, we'll take a look at the mechanism for acetal formation. Since this reaction is run under acidic conditions, the oxygen of the carbonyl is going to be protonated first. Now usually, with these types of reactions, the alcohol involved, which we're using methanol, has been protonated first by the acid. So now we have methanol with an extra H, and this is going to act as the proton source. So in our first step, the oxygen is going to take the H from the protonated methanol and give the electrons back to our oxygen. Now we have our positively charged oxygen, which is a much stronger electrophile and is now more attractive to the methanol nucleophile. So in this step of the mechanism, we are attacking the carbonyl carbon and kicking the electrons up onto oxygen. So this is very similar to what we saw in the previous video. Now, after the nucleophilic attack, the oxygen is going to have a positive charge. Now, we're going to get rid of that positive charge by taking away its proton. Now, the thing that can take away the proton is another molecule of methanol. So in these reactions, we have extra methanol all over the place, and the methanol can act as a weak base as well as a weak nucleophile. So it'll take the H, giving the electrons to the oxygen atom. Now this is going to create an intermediate known as a hemiacetal. And I'm going to go ahead and put this hemiacetal in brackets. Hemiacetals are very unstable for the most part. There's some that exist naturally, and I will give examples of those in a little bit. But this example of a hemiacetal is highly unstable, and you actually cannot isolate it. So the reaction must continue to create the full acetal. Okay, so from our hemiacetal, we're going to continue with the acetal formation. Now the methanol that we just used as a weak base can now act as another proton source. So our oxygen attached to the H is going to go and grab that extra H from our protonated methanol. And what we're doing here is we're turning our OH from a bad leaving group into a good leaving group. So now we have a good leaving group in the form of water. So the oxygen containing our methyl, our R group, is going to donate its electrons to create a double bond, and at the same time it's going to kick off the water as a leaving group. So this is the point where we lose water in the reaction. Now we have an intermediate that's acting very much like the super strong electrophile that we created after the first step. So now we have a C double bond O with a positive charge on our oxygen. So we're kind of creating a new carbonyl in the middle of this mechanism. Now this is going to be susceptible to nucleophilic attack by the blue methanol. So it'll come in, again, attack this carbon, and kick the electrons up onto the oxygen. Then our last step is going to be removal of the extra H to give the electrons back to oxygen and make it neutral again. Another molecule of methanol, which we have floating around in the solution, can act as the weak base, can take this extra H, giving the electrons to the oxygen. That is our full mechanism for creating an acetal. With ketones, it's important to note that the reactants are actually favored when it comes to acetal formation. What that means is the carbonyl of a ketone is actually much more stable than the acetal form. So in general, this reaction doesn't want to proceed forward. It wants to stay in the ketone form. Now, what we're going to do in order to allow this reaction to occur is take advantage of the other byproduct that forms as a result of acetal formation, and that is water. Now we can manipulate the equilibrium by removing water. If you take away the product, the equilibrium will shift to form more products. So that's exactly what we're going to do. During the acetal formation of a ketone, water is actually removed during the reaction in order to drive the equilibrium forward. So you're often going to see acetal formation reaction conditions written like this. So we have our ketone, we have our acid catalyst, we have our alcohol or water, and then we also see minus H2O. So this means that the water is being removed during the reaction. So it's actually a part of the reaction conditions. And that is how we form the acetal of a ketone. Now with aldehydes, this is not a necessary step because the aldehyde carbonyl is not as stable as the acetal, and so the acetal forms very readily. In our mechanism for acetal formation, we saw that hemiacetals are highly unstable and cannot be isolated. There are some cases where hemiacetals are actually stable, and that's when they are incorporated into a ring. So a hemiacetal, by definition, is when we have an oxygen attached to an OH and an oxygen attached to an R group connected to the same carbon. So this here is the hemiacetal. Now this is stable and this molecule can be isolated. Many carbohydrates, including glucose, also contain hemiacetal functional groups. So with glucose, the hemiacetal will form here. So we have our oxygen attached to an R group and an oxygen attached to an H that are attached to the same carbon. So this is the hemiacetal functional group. So when it is enclosed in a ring, it is very stable and would be able to be isolated. The next reaction we'll talk about is imine formation. With imines, we're going to be using aldehydes or ketones, and again, I'll use a cyclic ketone as our example, and we will be reacting it with an amine. Now, it's very important that we use ammonia or primary amines only. Now, this reaction is also going to run under acidic conditions, so you will have an acid catalyst. And ultimately, you're going to form this type of functional group, which is called an imine. So essentially, we replace the oxygen of the ketone with the nitrogen as well as the R group attached to it. We also form water. Now, this type of product is the type of product we formed when we made our derivatives in our unknowns experiment in lab. So this is the exact mechanism that we followed as you were preparing your derivatives. We'll take a look at the mechanism on the next slide. With imine formation, even though it's running under acidic conditions, the first step in the mechanism is actually going to be the nucleophilic attack by the nitrogen. The reason that this differs from typical mechanisms involving acidic conditions is because nitrogen is a stronger base than oxygen. Thus, if we were to protonate this oxygen first with a hydrogen, the nitrogen would actually act as a base and remove that H rather than act as a nucleophile. So in this type of mechanism involving nitrogen, the nitrogen must act as a nucleophile first. So go ahead and take a look at our nucleophile. We have a primary amine attached to a methyl group. Now the nitrogen has its lone pairs. It's going to come over and attack the carbonyl carbon, giving the electrons to the oxygen. Now after the attack, the nitrogen will be positively charged and the oxygen will be negatively charged. So the next step is going to be protonating this oxygen. And the reason this is going to occur first is because under acidic conditions, we want to avoid the negative charges as much as possible. So now our oxygen will come over and will take the H from the acid. Now we have a bunch of amines floating around in the solution which are capable of acting as bases. So one of the amines will come and remove the extra H and give the electrons back to the nitrogen. Now this intermediate is called a carbenolamine. And it's very similar to a hemiacetal. Now it's not as unstable as a hemiacetal, so technically we could isolate this amine. So now for our next steps, it's going to be similar to what we saw with the acetal formation. We have an OH that we need to turn into a good leaving group. So the red amine that just acted as a base now has an extra proton. And it is positively charged. So our oxygen can come and take that extra proton, giving the electrons back to the nitrogen, and now we are turning our bad leaving group into a good leaving group. So similar as to what we saw with the acetal formation, the nitrogen has lone pairs that it can donate to form a double bond with the carbon and at the same time kick off water as our leaving group. Now, unlike the acetal formation, we're not going to do another nucleophilic attack. Now we have a nitrogen with a positive charge, and it also has a hydrogen available to be deprotonated. So since this solution is surrounded by nitrogen-containing molecules, which are good bases, we can easily remove this H. So we'll have another nitrogen come in, remove the H, and give the electrons to the nitrogen. And at this point, we have formed our imine. So with this, we have to use a primary amine or ammonia, and that's because we will be removing hydrogens from the nitrogen at 2 points in the molecule or in the mechanism. So we remove a hydrogen here, we also remove a hydrogen here. So with secondary and tertiary amines, we don't have enough hydrogens that can be removed. Now, depending on what's attached to the amine, we can form different types of products. So for instance, if we take a ketone, react it with a primary amine that's attached to an alcohol group, the product that forms looks something like this, and this is called an oxime. We can also react it with a primary amine that's connected to another primary amine. This molecule is known as hydrazine. And the product that forms is known as a hydrazone. Now, hydrazones are extremely useful in synthesis. And that's because they can be used in the Wolff-Kishner reduction to ultimately get rid of these nitrogens and the carbonyl. So the Wolff-Kishner reduction involves a hydrazone as well as reaction conditions of potassium hydroxide in water and heat. Ultimately, we're going to get rid of the hydrazone functional group and replace it with H's. So this is a very good reaction for getting rid of carbonyls of aldehydes or ketones. Let's go ahead and take a look at the mechanism of how this works. So we'll start with our hydrazone. And we've got two H's attached to the nitrogen at the end. Now we have basic conditions, and hydroxide is a strong base. So the hydroxide will come and take one of the H's from the nitrogen, giving the electrons to the nitrogen. Now the nitrogen has a negative charge. Now these lone pair are allylic. They are one bond away from a double bond. So we're actually going to see resonance occur. We have the electrons come over, form a double bond between the two nitrogens, and give the electrons as a lone pair to the carbon. Now, so since this is resonance, I'm going to draw a double-headed arrow and the second resonance structure. Now we also have water in this mixture. So at this point, water is going to act as a proton source. We'll take one of the H's and we'll create a new hydroxide ion. I'm going to put these in brackets since they are resonance structures. So that's how we get the first H on the carbon. So then the same thing's going to happen. We're going to have hydroxide come in, remove the last H from the nitrogen, give the electrons to the nitrogen atom. Now we have a nitrogen that's negatively charged. It is going to donate its electrons to create a triple bond, which will cause the nitrogen-carbon bond to break, and we're going to give the electrons to the carbon. Now this is not a resonance structure because instead we are forming nitrogen, or N2. Any chemical reaction that forms nitrogen is extremely favorable. So this is the step in the mechanism that drives the entire reaction forward. Now we're going to use water again to protonate this carbon atom. And ultimately create our reduced products. So the Wolff-Kishner reduction can completely get rid of carbonyls via a hydrazone intermediate. Next, we'll talk about enamines. Enamines are very similar to imines. They will involve nitrogen as a nucleophile, but the difference is with imines, we use ammonia or primary amines, and with enamines, it involves a secondary amine only. So that means a nitrogen attached to two R groups can only be used to form enamines. Now, similar to imines, this will involve an acid catalyst, and ultimately we will form a product that looks like this, as well as water. So the reason this is called an enamine is because you have an alkene, as well as an amine as a result of this reaction. So I'm not going to go through the entire mechanism for an enamine. I ask you to try the mechanism based on the imine mechanism and then compare it to the one that you see in the book. Now we saw that acetals, imines, and enamines can all be formed from aldehydes or ketones. Now acetals, imines, and enamines can also undergo hydrolysis to be turned back into those aldehydes or ketones. So for example, if we take an acetal containing 3 carbons and we take an imine containing 3 carbons and an enamine containing 3 carbons, treating all of these with H3O+, we'll turn them back into a 3-carbon containing carbonyl, such as this ketone here. Now the book contains an example of the mechanism of this process for an acetal. Essentially, it's just the reverse reaction of acetal formation. I will go ahead and go through the mechanism for turning an enamine back into a carbonyl. And then it's up to you to kind of figure out how an imine would ultimately undergo hydrolysis as well. So in the next slide, let's focus on the enamine mechanism. So we'll go ahead and take a look at the hydrolysis of this enamine. Now hydrolysis will always be the reverse reaction of how the functional group formed in the first place. So in an enamine, the double bond is the last thing to form. So it's going to be the first thing to go away with hydrolysis. So the nitrogen has lone pairs. It's going to donate its lone pairs and create a double bond between itself and the carbon. That's going to push these pi electrons to act as a nucleophile and take the H from the hydronium. So now we will have a nitrogen with a positive charge. We've just added an H to the ring. And now our goal is to ultimately replace this entire group with an oxygen. So now we've just used water, created water, when we took away the hydronium's proton. So now the water is going to act as a nucleophile, and it's going to come in and attack the carbon and kick the electrons up onto nitrogen. Okay, now we are going to remove one of the H's from our oxygen atom. And we can have water come in and do that as well. Now ultimately, we need to get rid of the nitrogen. So the nitrogen is going to be turned into a better leaving group by being protonated by the hydronium we just formed. So we'll take that H, give the electrons to the oxygen, and we are turning it from a bad leaving group into a good leaving group. So now our oxygen is going to donate its lone pairs to create the double bond and kick off the nitrogen. So now we have our original secondary amine again. Then our last step is to remove the H from the oxygen and create our original ketone. So we're just doing all the steps, but in reverse, to do the hydrolysis of acetal, imine, or enamine.